We'll begin our discussion of the normal distribution by talking about the standard normal distribution. The properties of the standard normal distribution include, let's get that, there we go. The first one is that the graph is bell-shaped. The next property is that the mean is 0. So we're standardizing the normal distribution. In this particular one, the mean is always 0. And our standard deviation, let me fix that. I didn't quite get that right. Okay. Our standard deviation, sigma, is 1. And finally, same thing we've been saying is that the total area under the curve is equal to 0. Okay, so we still have that correspondence between probability and area. And recall that we said all continuous probability distributions are density curves. And so let me say that. Continuous probability distributions are density curves. And density curves are histograms. So we recently spoke about the uniform distribution with our probability on the vertical axis, our random variable x on the horizontal axis. And so this is a density curve where all of the bars, if you will, are the same height in our histogram. Okay? So all of the bars have equal height in a uniform distribution. Then with the normal distribution, just in general, when we talked about the bell-shaped symmetrical curve, well, it may be, let me sketch here so you can get an understanding. Hard to think of this as a histogram, but if we could break this down into minuscule little bars, let's see, then we could relate this to a histogram. And I'm not quite getting it right. I need to cross right there. So let me try that again. But the idea is that if you could make these thinner and thinner and thinner, right, then what you would find is you have these bars like a histogram, where still the height is the probability. I'm not doing a very good job of this, but maybe you get the idea. If you just think about refining these bars to as thin as possible, then they can start taking that shape where we end up with a symmetrical graph. But think of this also as a histogram. But see, we can see the connection here between the area and the probability and the relative frequency. Okay, so now we want to talk about, this is just in general normal distribution. Let me write that down, normal distribution. But right now we're talking about a special normal distribution called the standard normal distribution. So let's look at that one. Hopefully I can draw this a little bit better. All right, so with the standard normal distribution, remember we just said that the mean is 0. So right here in the middle is 0. And so then we have our bell-shaped curve. Hopefully I can peek about where I put the middle. Okay. And right here is our mean with the two symmetrical pieces. So if the area under the curve is equal to 1, then I know that the area here must equal 0.5 because we said it's symmetrical. So half of the area is over here and half of the area is on the other side of the mean. And what that just tells us is there's a 50% probability or a 0.5 probability that we get a value above the mean and a 0.5 probability that we get a value below the mean. And that should make sense. Okay, let me label along my horizontal axis. We said the standard deviation, sigma, is equal to 1. So I can go out here to 1, and then 2, and then 3. These are my standard deviations. Okay, 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean. That should sound familiar. What are we talking about there? We're talking about z-scores, right? Here is 1 standard deviation below the mean, 2 standard deviations below the mean, 3 standard deviations below the mean. So let me just mark these. These are what we call our z-scores. Let me change colors here. So these are z-scores. And let me label this. I didn't label it, but this is our mean of 0 right there. So remember that z-scores tell how many standard deviations a particular value is above or below the mean. So the mean has a z-score of 0 because it is 0 standard deviations above or below itself, right? That makes sense that it would then have a z-score of 0. So the z-scores are located along the horizontal axis. We could continue out to +4, +5, -4, -5 on the horizontal axis, but since our curve gets very close to the horizontal axis at that point, there's just a teeny bit of area out that way. It's extremely small, and there's no real point to go out much further than 3 standard deviations. And of course, most of the data, and thus most of the area, is centered around the mean. Okay, so this is our standard, let me label, this is our standard normal distribution. In this case, where the mean is 0, the standard deviation is 1. The other things continue to hold. The area under the curve is equal to 1, and therefore the area on either side of the mean is 0.5, and it's symmetrical, so both sides are 0.5.